Welcome to this deep dive. Today we're doing something a little different. We are looking at a really detailed breakdown we have of scooter mechanics.
Yeah, which sounds super niche, I know, but it is actually fascinating.
It really is. And the mission for this deep dive is to unravel this modern mechanical mystery. Like, how does a scooter accelerate continuously without you ever having to manually shift gears?
Right, and why does it absolutely refuse to stall out when you come to a dead stop, even though there's no clutch lever?
Exactly. Because think about it. You twist the throttle on a scooter and, it just goes. You let off the throttle and it slows down.
Yeah, there are no clunky gear changes.
No jerky starts at all. You
Yeah.
don't have a clutch to manage. And somehow, no matter what you do, the engine just never stalls. It just hums along.
It feels completely effortless to the rider, right?
Right.
Like the operation is designed to be totally invisible.
Honestly, when you are weaving through traffic, it feels incredibly simple, almost mindless to operate.
But I mean, that feeling is essentially just a user interface trick.
Wait, a trick.
Yeah, it's hiding this massive, highly complex physical contradiction that's happening right under the seat.
Okay, let's unpack this. Because to understand why the system is so genius, we first have to understand the fundamental problem it's trying to solve.
And the source material provides a brilliant window into this. What's sitting between the engine and the rear wheel of a scooter isn't just a basic chain or a fixed axle.
Right, it's not a bicycle.
Exactly. It is one of the most elegant, mass-produced, continuously variable mechanical systems in the world.
And the most striking part to me is that it achieves all of this without a single computer chip, sensor, or electronic actuator. Zero.
Which is wild. To appreciate how wild that is, we need to look at the two main players in this system, right? The engine and the rear wheel.
Yeah, the source makes it very clear that internal combustion engines are just incredibly needy.
Very needy. They have extremely strict demands just to keep running. An internal combustion engine only produces usable power within a very specific, narrow band of speed.
Because it relies on a delicate rhythm.
Right. Yeah, a delicate rhythm of taking in air and fuel, compressing it, and igniting it. If the engine speed drops too low, well, that rhythm breaks down.
And then what happens?
The combustion becomes irregular, torque basically falls off a cliff, and the engine stalls out.
But, you can't just let it spin infinitely fast either, right?
Far from it. If the engine speed gets too high, the internal friction, the heat buildup, and just the sheer mechanical stress of pistons flying up and down,
It's just break.
it will literally tear the engine apart. Yeah.
Wow. The breakdown points out that for a typical small scooter engine, this happy operating window, the power band, is roughly between 3,000 and 8,000 revolutions per minute, RPM.
Right.
So the engine is screaming away in that tight little window. But meanwhile, the rear wheel is dealing with the unpredictable reality of the street.
Exactly. The wheel has a totally different set of requirements. It needs to operate at speeds that range from absolute zero when you're sitting at a stoplight all the way up to highway speeds.
Which might require the wheel to spin at thousands of RPM.
Right. So we have an engine that demands to spin at thousands of RPM just to stay alive, and a wheel that is currently sitting at 0 RPM because, you're stopped for a pedestrian.
That's a huge disconnect.
And this contradiction is why a fixed mechanical connection simply cannot work.
Like, imagine if you bolted the engine directly to the rear wheel with a fixed ratio optimized for top cruising speed.
Oh man, the moment you open the throttle from a dead stop, the heavy mass of the scooter and the rider would just resist moving.
And that resistance would be transferred straight back to the engine, right?
Yep, it would drop its RPM below that critical threshold, and it would instantly stall.
It's like trying to start riding a 21-speed bicycle, but you're stuck in the absolute highest, hardest gear.
Oh, that's a perfect analogy.
You put your foot on the pedal, you push with all your weight, and you just tip over. You don't have the mechanical leverage to get that mass rolling.
Conversely, think about what happens if you use a fixed ratio designed exclusively to help you pull away from a stop, like first gear on that bicycle.
Oh, you'd pedal like a maniac. Your legs would be an absolute blur.
But you'd be moving at a walking pace.
Right. The scooter would lurch forward with plenty of torque, but the engine would hit its physical limit, just screaming at its maximum RPM, long before you even reached 50 kilometers per hour.
Yeah, you would max out the engine before you could even merge into traffic.
So motorcycles and cars solve this with a manual gearbox. You have a set of discrete, separate gears.
Right, inside a transmission case.
And as your speed increases, you manually pull a clutch lever to disconnect the engine, manually select the next gear up, and reconnect it.
Which keeps the engine happy in its power band. But scooters don't have a gear shifter. They use a CVT, a continuously variable transmission.
And the key word there is continuously, right?
Absolutely. A CVT does not step from first gear to second gear to third gear.
So it's not a staircase.
No, it sweeps smoothly across an infinite number of ratios within its physical limits. It's constantly adjusting to keep the engine in that 3,000 to 8,000 RPM sweet spot.
I'm trying to picture this honestly. If there are no discrete metal gears snapping into place, what is actually connecting the engine to the wheel to transmit the power?
According to the breakdown, it starts with a component called the primary variator.
The primary variator, so this is the driving assembly.
Yes, it's mounted directly to the engine's crankshaft.
Wait, let's make sure we're on the same page for everyone listening. The crankshaft is the main shaft coming out of the engine itself.
That's right, it's the main output shaft. Whatever the engine is doing, the crankshaft is doing, and therefore the primary variator is doing.
Okay, got it. And the geometry of this variator is what I find so hard to visualize.
It can be tricky.
The source describes two faces shaped like truncated cones. So picture a regular cone, but the pointy tip is sliced off.
Yeah, flat on top.
And these two conical faces are pointing toward each other, creating a V-shaped valley between them. And running right down in that valley is a V-shaped drive belt.
Right. Those conical faces are sometimes called sheaves. They're the physical interface for the belt.
And the belt itself isn't just regular rubber, is it?
No. The source notes this belt is usually made of heavily reinforced rubber, packed with embedded cords, often Kevlar or similar materials.
Wow, Kevlar.
Yeah, it has to withstand massive tension.
But if they're just spinning cones, how does that actually change the gear ratio?
Well, the secret is that the distance between those two conical faces is not fixed. One face is securely bolted to the crankshaft, but the other face can slide back and forth along the shaft.
Ah, I see. And because the belt itself has a V-shaped profile that matches the angle of the cones, when that movable face slides closer to the fixed face, the valley gets narrower.
Exactly. The belt is physically squeezed, and since it can't compress, it has nowhere to go but up.
It gets forced outward toward the outer perimeter of the cones.
Think about the geometry of a circle here. When the belt gets pushed outward, it's forced to run at a much larger diameter.
It creates a larger circumference.
Right. And when the faces pull apart, the valley widens, and the belt drops back down deep into the groove near the central shaft, running at a much smaller diameter.
So when the belt is at a small diameter, one spin of the engine only pulls a tiny amount of belt.
Yes.
That's your low gear, lots of leverage. But when the belt is pushed to the outer edge, one spin of the engine pulls a massive length of belt. That's your high gear for top speed.
You've got it. That changing circumference is the entire basis of the gear ratio change.
Hold on, though. If there are no computer chips telling this thing when to shift, and no little electric servo motors pushing these conical faces back and forth, how does the variator know when to push the cones together?
It relies entirely on centrifugal force.
Right, just pure physics.
Pure physics. Behind the movable conical face, hidden inside a housing, there are several small cylindrical masses. These are the roller weights.
Okay.
And they sit inside specifically designed ramped channels.
Here's where it gets really interesting. I was reading this part of the source, and it reminded me of being on a playground merry-go-round. Oh, that's a great way to think about it.
When a merry-go-round is just barely turning, you can easily stand right in the center. But as the older kids spin it faster and faster, you feel this invisible hand pulling you outward.
Yeah, you are physically pushed toward the edge, and you have to hold on for dear life.
Exactly.
That invisible hand is centrifugal force, and that is exactly what acts on those roller weights.
So at low speeds.
Right. At a low engine RPM, when the scooter is just idling, the centrifugal force is incredibly weak. The roller weights just sit passively near the center of the variator.
So they aren't pushing on anything.
Because they aren't exerting any pressure, the two conical faces stay far apart, and the belt rests deep in the groove at its smallest diameter.
But then you twist the throttle, the engine revs up, the crankshaft spins faster, taking the variator with it.
And as the RPM climbs, the centrifugal force multiplies. It throws those cylindrical rollers outward toward the edge of the assembly.
But remember, they're trapped inside ramped channels. Yes. So they can't just fly straight out. The ramps force them to move sideways as they move outward.
And that sideways movement physically pushes the movable conical face across the shaft directly toward the fixed face.
You're squeezing the belt.
Squeezing the belt. The faster the engine spins, the harder the rollers push outward against their ramps, the tighter the faces squeeze together, and the higher up the belt rides.
It smoothly and seamlessly changes the ratio.
That is just a beautiful chain reaction. I mean, it's shifting gears simply by utilizing the physical reality of its own spinning momentum.
It really is.
Yeah,
But putting tension on a belt is only half the story.
right. The other end of that belt has to connect to the wheel.
And according to the source, that brings us to the secondary assembly.
Okay, so what happens back there?
What's fascinating here is how the secondary assembly, which is mounted on the rear wheel shaft, it mirrors the primary variator, but it behaves in a completely opposite manner.
So there's another set of conical faces, another valley for the belt to ride in, but what controls these faces? There aren't roller weights in the rear, right?
No roller weights in the back. The secondary assembly is controlled by a massive, heavy-duty torsion spring.
Could you clarify torsion spring for me? Are we talking about a spring that compresses like a pogo stick or something else?
Well, a torsion spring provides resistance against twisting, but in this specific application, it's also configured as a compression spring.
Okay.
It sits behind the movable face of the secondary assembly, constantly pushing the two rear cones together with significant force.
So let's map this out for a second. When the scooter is stopped or moving very slowly, the engine is barely spinning.
Right.
The rollers in the front haven't pushed outward yet. The front cones are wide open, and the belt is resting deep at a small diameter.
Yep.
But in the rear, that big spring is squeezing the secondary cones tightly together, forcing the belt out to the absolute largest diameter.
Small diameter in the front, large diameter in the rear. That is the mechanical definition of a low gear ratio.
Giving the engine maximum leverage to overcome the stationary mass of the scooter. But as you accelerate, the front rollers fly out, the front cones squeeze together, forcing the belt to a larger diameter.
So it's basically a mechanical tug of war.
Right. The engine side is wedging the belt outward, demanding more slack. But where does that slack come from if the belt is a fixed length?
The front variator essentially steals the slack from the rear.
Steals it.
Yeah, as the belt is forced to a larger circumference in the front, the tension on the belt skyrockets. That tension literally pulls against the secondary assembly.
Oh, I see.
The belt acts as a wedge, pulling the two rear conical faces apart, fighting directly against the pressure of that massive torsion spring.
So as the belt climbs higher on the engine side, the physical tension drags it deeper into the groove on the wheel side.
You've got it. The secondary assembly isn't merely a passive receiver. By yielding to the tension and dropping the belt to a smaller diameter, it drastically multiplies the ratio change that started on the primary side.
Expanding the range.
Right. It extends the total gear range the scooter can achieve, creating a continuous push-and-pull balancing act dictated entirely by centrifugal wedge forces and spring tension.
Okay, the mechanical tug of war makes perfect sense now. We've solved how the CVT sweeps through the gear ratios.
Yeah.
But, this actually brings up a huge contradiction based on what we just discussed.
What's that?
If the belt is always under tension, connecting the front pulleys to the rear pulleys, why doesn't the scooter launch forward when I'm just sitting at a red light?
Oh, right.
If the engine is running, the belt is moving, why don't I stall?
Ah. For that, we need to look at the centrifugal clutch, which is cleverly housed entirely inside the back of that secondary assembly at the rear wheel.
Let's quickly define what a clutch's job actually is and why stalling happens. Stalling occurs when a mechanical load is dumped onto an engine abruptly, right?
It's like faster than the engine can build up the RPM and torque to handle it.
Yeah. If you've ever driven a manual transmission car and let your foot off the clutch pedal too fast at a red light, you know the feeling.
The car jerks, the engine chokes, and it goes dead silent.
Exactly. Because you forcefully coupled the stationary mass of a 2-ton vehicle to an engine that was barely idling.
The engine just did not have the rotational momentum or the power output to sustain its combustion cycle under that instantaneous burden.
But the scooter's centrifugal clutch operates under a strict no stalling rule. It refuses to let that happen.
It manages this by utilizing centrifugal force a second time, but for a completely different purpose.
Which is?
Controlling mechanical engagement. Inside the housing of the secondary assembly, there are several heavy clutch shoes made of friction material, similar to brake pads.
And these shoes are mounted on a plate that is spinning with the rear pulleys.
Correct. But surrounding these spinning shoes is a steel cylinder called the clutch drum.
Okay, drum.
The drum is the component directly splined to the rear wheel axle.
Oh, I see. So the shoes spin with the belt, but the drum is tied to the wheel.
Now, at idle RPM, there are stiff little retention springs hooked onto those clutch shoes.
Skiff springs.
Incredibly rigid. They hold the shoes pulled inward, completely retracted away from the inside walls of the clutch drum.
Meaning there is a physical air gap between the shoes and the drum.
An absolute physical disconnect. The engine is idling, the primary variator is spinning, the belt is running over the secondary assembly, and the clutch shoes are spinning.
But because they aren't touching the drum,
Absolutely zero torque is transferred to the rear wheel axle.
the scooter just sits there, the engine runs freely, but then you twist the throttle.
Yep, the engine RPM rises, the belt moves faster, spinning the secondary assembly, and those retracted clutch shoes faster and faster.
And just like the roller weights up front, the invisible hand of centrifugal force takes over.
Exactly. As the shoes spin faster, they desperately want to fly outward.
But those stiff springs are holding them back?
For a bit, eventually the rotational speed crosses a specific threshold. The centrifugal force pulling the shoes outward finally overcomes the mechanical tension of those stiff little retention springs. The shoes hinge outward, bridging the air gap, and the friction material presses hard against the inside of the steel clutch drum.
So the system literally uses its own spinning momentum as the trigger.
Yes.
It can't stall, because the very condition that would cause a stall low RPM under load prevents the connection from happening in the first place. That's incredibly elegant.
It acts as a foolproof, physics-enforced anti-stall device. And as the RPM climbs, the shoes don't just snap fully engaged.
They ease into it.
They slip slightly against the drum at first. The friction gradually applies the load precisely as the engine builds enough torque to handle it.
The system protects the engine from the rider's demands. Like you can rip the throttle wide open from a dead stop, and the clutch will slip just enough to let the engine jump up into its power band.
Right, before fully locking up against the drum and sending you forward.
It self-regulates entirely based on rotational physics.
Exactly.
Which begs the question, if the entire sequence of events is dictated by fixed physical properties, what happens when we start altering those properties? The source goes into some fascinating detail about tuning and wear in the real world.
This is a massive topic for scooter mechanics. Because the system relies on proportional mechanical reactions, making a microscopic change to one component causes a massive ripple effect through the whole transmission.
Let's revisit those roller weights in the primary variator. They aren't arbitrarily chosen, are they?
Not at all. The source notes that a change of just 1 or 2 grams per roller produces a drastically different acceleration profile.
And a gram is roughly the weight of a paperclip.
Just a paperclip. So if you open the variator and replace the factory rollers with lighter rollers, think about how that changes the physics.
Okay. Lighter masses generate less centrifugal force at a given speed.
Meaning they need a much higher engine RPM to generate enough force to push the variator closed against the resistance of the belt and that big rear spring.
So the transmission shifts later. It artificially holds the transmission in a lower gear ratio longer, letting the engine rev much higher during initial acceleration.
Right. Riders often do this to get a punchier, sportier launch off the line, keeping the engine at the absolute peak of its power band.
But what if you install heavier rollers?
Well, heavier rollers generate strong centrifugal force very easily. They get thrown outward early at lower RPMs.
So the variator shifts quickly.
Yeah, shifting the scooter into a higher gear ratio sooner. It smooths out the acceleration, but might make it feel a bit sluggish, like shifting into 5th gear too early in a car.
If we connect this to the bigger picture, it reveals why maintenance on a CVT isn't just about preventing a catastrophic breakdown.
It is fundamentally about maintaining the physical geometry of the transmission.
I want to focus on the drive belt for a second. The stress on that rubber belt must be unbelievable.
It's immense.
It isn't like a steel motorcycle chain locking securely into metal gear teeth. It transmits all the horsepower and torque to the rear wheel entirely through the friction of its sidewalls.
It is continuously being violently wedged and squeezed between metal conical faces while simultaneously bending and flexing tightly around 2 sets of pulleys.
Pulleys that are constantly changing their diameter at thousands of RPM.
Right.
Wait, if it's transmitting all that power purely through friction, the sides of the belt have to wear down over time, almost like a pencil eraser rubbing on paper.
That's exactly what happens.
And if the sides wear away, does that mean the belt physically gets thinner?
It absolutely gets thinner. The rubber and embedded cords slowly degrade and shed material.
But if the belt gets thinner, wouldn't it sink deeper into the V-shaped valley between the cones?
Yes.
Does a worn belt actually change your gear ratio?
It does. A worn belt alters the effective ratio range of the entire CVT.
Wow.
Because a narrower belt sits deeper in the groove, The movable conical face has to travel further across the shaft just to squeeze it to the same starting diameter.
Oh, that makes sense.
And at the top end, even when the variator is fully closed, a thin belt simply cannot be pushed all the way out to the maximum circumference.
So a degraded belt creates symptoms that a typical rider might completely misdiagnose.
Constantly. They'll notice sluggish acceleration, or they'll be on the highway and realize the engine is screaming, but their top speed has suddenly dropped by 10 kilometers per hour.
And they panic, thinking the engine is losing compression or failing.
But the internal combustion engine is likely perfectly fine. The transmission is just physically incapable of achieving its highest gear ratios anymore.
Because the geometry of the belt has deteriorated.
Exactly. Replacing a worn scooter belt isn't just swapping a part. It's restoring the geometric mathematical ratios required for the system to function.
And it isn't just the rubber that wears out, right? The metal faces of the sheaves themselves can suffer over thousands of kilometers.
Yeah, the belt constantly rubs up and down the faces of those cones. Over time, particularly if a rider holds a constant cruising speed for years, the belt can wear a physical groove into the metal face.
Which means the roller weights try to push the belt to a higher ratio, but the belt gets stuck in that worn-out groove.
That's right. Additionally, the CVT housing is only semi-sealed because it requires airflow to cool down all that friction-generated heat.
Oh, so dust gets in.
Ambient dust, road dirt, moisture. It all gets inside. That contamination alters the coefficient of friction on the cones.
Meaning the belt slips, excess heat builds up, the rubber glazes over, and wear accelerates exponentially.
You've got it. The source even mentions temperature plays a major role. On a cold morning, the drive belt is physically stiffer. It's less compliant.
A stiff belt resists bending around the small diameter of the front variator at low speeds.
Right. It fights the geometry, changing how torque is transmitted until the friction warms the rubber up, making it pliable again.
That perfectly explains why a scooter always feels a little bit sluggish or hesitates slightly during the first few minutes of a cold ride.
Yep.
You are literally waiting for the physical properties of the rubber to change. Speaking of physical properties, what dictates the absolute limits? Like, how fast can the system theoretically go?
Well, there are absolute mechanical limits.
Mm.
People often wonder what governs top speed on a scooter.
Yeah.
Once the primary variator has squeezed fully closed and the roller weights have reached the absolute end of their ramped channels, the belt is pushed out to its maximum possible diameter.
The ratio is physically locked at that point. It cannot change anymore.
From that moment on, the transmission operates like a fixed gear.
Yeah.
If you want to increase your speed, the engine just has to spin faster.
But eventually, the aerodynamic drag of pushing the rider's body through the wall of air equals the maximum horsepower the engine can physically produce at its RPM limit.
Right. So top speed is just the mathematical intersection of engine power and aerodynamic drag, dictating the limit once the variator is maxed out.
And conversely, the pulling power off the line is strictly limited by how far apart those variator faces can physically separate before hitting the housing.
Exactly.
So what does this all mean? When we step back and look at the entire system detailed in the breakdown, it is an incredibly profound chain of mechanical causation.
It really is. Every single action is a continuous, proportional physical reaction.
Look at the chain of events. It starts with a twist of the rider's wrist. The throttle cable opens the intake. That dictates the combustion rate and the engine RPM.
Right. And the RPM dictates the exact amount of centrifugal force acting on the rollers.
The rollers dictate the width of the front cones.
The front cones dictate belt tension.
Belt tension overpowers the rear spring.
The rear spring dictates the final diameter.
And the output ratio finally reaches the rear wheel, provided the centrifugal clutch has spun fast enough to engage the drum.
Every single link in that chain is a pure mechanical consequence of the link before it.
And conceptually, this design hasn't fundamentally changed since the iconic European scooters of the 1950s.
Sure, the materials are vastly superior today. We use advanced composite plastics for the rollers instead of steel, and Kevlar reinforced rubber for the belts.
But the physics are identical. You trade the discrete control of manually selecting your own gears for the seamlessness of continuous variation. You trade rider authority for a system that manages itself automatically.
It raises an interesting point regarding modern engineering. We have built our contemporary world almost entirely around digital control.
Yeah, we rely on complex electronic brains to make billions of binary decisions a second to manage our vehicles and machines.
Yet here is a purely mechanical system that self-regulates flawlessly.
Yeah.
It responds dynamically to the continuous physical inputs of its environment, centrifugal force, spring tension, friction, rotational mass, without executing a single line of code.
It makes you wonder, where else in our increasingly complex, algorithm-driven world might we actually benefit from stepping back and returning to simple, continuous, self-regulating physical systems?
That's a fascinating thought to leave on.
The next time you see a scooter zip effortlessly through traffic, or the next time you twist that throttle yourself and feel it just go, you'll know exactly what is happening under all that plastic. It isn't magic. It's just a brilliantly elegant tug of war of pure physics.